Okay, we're going to continue our discussion of Maxwell's equations, and our goal, of course, is to understand Maxwell's equations in something called reciprocal space. However, admittedly, we're working mostly right now in real space to get a firm grip on all of the elements of Maxwell's equations that we're going to need, and then we'll spend our time moving into reciprocal space. So we're still actually in real space, and the goal today is to start down the road of the potential formulation of Maxwell's equations. And the potential formulation is basically the idea that we can, which we should all be familiar with, that the magnetic field can always be expressed as the curl of something we call the vector potential, and that likewise the electric field can always be expressed as the gradient of a scalar field plus the way we write it is minus the time derivative of the same vector potential. And so we have to understand and derive this very solidly. Now, the way I'm going to do it is in tremendous detail. First of all, you can get by just fine, by the way, if you just accept this, that there's this thing out there called the vector potential. Notice I'm not using little vector indications anymore. We know this is a vector. The curl must be of a vector field, so that needs to be a vector. The gradient must be of a scalar, otherwise it would be a divergence, right? Likewise, we know that this is a vector potential. You could just accept this and kind of move on. It is important to understand that the reason this is true is because the divergence of B, right? The divergence of B equals 0, and when the divergence of a vector field is 0, we can express it as the curl. That's sort of the way it's of the curl of some other vector field. That's probably as much as most people remember if they're a year or two away from E&M. But we are going to spend this lecture really focusing in on why this is true. So we get a good review of a lot of vector calculus, right? That's sort of the idea, to get a good review of vector calculus. And then in the next lesson, we'll flush this out. Just to make sure nobody's confused, this is a reproduction of a lesson where when I tried to do this demonstration, I actually confused my lesson about gauge freedom with the potential formulation. They're very closely related, and in fact, the mathematical concepts are literally intertwined. But I somehow got my wires crossed, and I gave a proof of this that's really more of a proof for gauge freedom. Anyway, so this is a repeat of a lecture that was done previously. All right, so with that in mind, let's begin. Okay, so I've prepared this mind map to get us through this collection of material. And we are going to begin by looking at this critical notion that the divergence of a curl equals 0, right? So the point being here is that if the curl of something is a vector, right? The curl of a vector field is another vector field. If I called that vector field B, at least it's plausible that if B was the curl of something, it will satisfy Maxwell's equations. It's sort of a bit of an if and only if, or a necessary but sufficient, right? It certainly would be sufficient for the magnetic field to be the curl of something. Is it necessary, however? Or is it always possible, right? Is it always possible to find an A that is equal to a B? And those are the questions I kind of want to wrestle with to be very thorough. But let's begin with just the basics, right? This principle here, we'll use the most simple, straightforward vector calculus to figure it out, right? The definition of the curl is the partial derivative with respect to y of the z component minus the partial derivative with respect to z of the y component of the vector. And that is the x component of this curl. And we can write this out for all three components, the y component and the z component. And we're going to take the divergence of that, which means that we take the x derivative of the x component, the y partial derivative of the y component, and the z partial derivative of the z component. And so you end up with these mixed partial derivatives. And a lot of these proofs in vector calculus is all about remembering that mixed partial derivatives commute. And so this xy partial of the z component of A is the same as the yx component of the z component of A, the yx derivative, the yx mixed partial derivative of the z component of A. So indeed, this and this cancel, right? So you have this cancellation here, you have the xz cancellation here, and you have the yz cancellation there, and it all ends up being 0. And it's 0 100%. There's no property of A that makes this 0. It's not like A has to have any special property to make this 0. The divergence of a curl of a vector field will be 0 100% of the time. So that's important. And then another important fact in vector calculus is that we use a lot, that you have to be familiar with, is the curl of a gradient. Now the gradient is a gradient of a function, but the gradient of a function is a vector. So you have the curl of a vector. So all that checks out. I love doing this domain and range stuff, right? You know, you treat this as though it's an operator, which is literally what it is. And you treat this as an operator, but the domain of this operator is the domain of functions, you know, of functions of x, y, and z, right? That's the domain. So you know that the domain is function, so it's operating on a function. The range is vector field, so it is a vector field. The domain of this is vector field, and its range is also vector fields, right? So you keeping that, that really serves you well, especially when you get into really abstract, you know, group theory stuff and you know, the really tricky tensor calculus. Knowing the domain and range of things is a really great way to make sense of weird equations. Anyway, to prove this is literally the same process in reverse, right? You first take the gradient of everything. Like, for example, the I component of this curl is going to be the y derivative, the curl, right? The y derivative of the z component of the gradient. Well, the z component of the gradient is partial z of f. And then it's minus the z component, or the z derivative of the y component of the gradient, which is partial y of f. So that's how you write, I guess to be consistent, I should put brackets right here. And if you pursue this all the way through, and you do it for each of the components, I wrote down I here, but what I mean, of course, is x hat, right? If you do this for y hat and you do this for z hat, you'll discover the exact same thing. You'll get cancellations. Well, actually, you can see it right here, right? The yz mixed partial of f and the zy mixed partial of f, that's 0 right away. It's actually even easier than this, right? Each one of these is 0. Each term of this is 0, right? And here's the definition, by the way, of the gradient. I don't know why. Sometimes I default to ijk. I don't know why I do that. It's confusing in this context, and I should be using x hat, y hat, z hat. I don't know why I do that. Okay, so those are the two important vector identities we're going to play with, and now we're going to try to understand how we can use this to create a vector field that will. Well, we're going to create a vector field and a scalar field together that will duplicate the electric and magnetic fields. So the place we'll start is we're going to go back to our Maxwell's equations, right? And what we start seeing is oh, well, look, we have curls, we have two curl equations and two divergence equations. And ultimately our plan is to exploit these and our vector calculus knowledge, which we just reviewed, and turn these 4 equations into 2 equations. So here 4, these are all first order differential equations, right? There's only first order differential operators buried in these divergences and curls, and this first order with respect to time here as well, right? So these are all 4 first order equations. Well, it stands to reason it might be possible to create 2 second order equations. And what we're going to start with is exploiting the fact that the curl of B is always 0. And we're going to ask ourselves, well, if we know that the curl of I'm sorry, did I say the curl of B? I meant the divergence of B is always 0. So if we know that can we find a vector field A such that B, this is true always, right? This is always true. So can we replace the curl of A with B, or can we replace literally B with the curl of A, right? This is Maxwell's equation, and we're just going to say, well, if we know the divergence of a curl is always 0, maybe it's B is the curl of something, right? So that's what we're going to now work on. All right, now let's begin the analysis that I was trying to do in the first iteration of this lesson, where I got completely spun around and confused and distracted into something else called the Helmholtz decomposition theorem, which we should cover. I should redo that. But what I'm trying to show you is that if the divergence of any vector field is 0, then that vector field can be expressed as a curl. And just to be very clear, this is different from saying that the divergence of a curl is 0, because the divergence of a lot of things could be 0, right? So B and B could be equal to one of those other things, right? Okay, I guess that's the idea. B could be one of the other things, not a curl. And I don't think people generally do this proof in normal E&M, and I like to kind of do these hyperlinks, ask these questions, and do these hyperlinks a little bit deeper than we normally probe. So let's do it. So how do we do this? We will start by saying, okay, well, first of all, what is the curl? How do we define the curl? And the curl is defined this way. This is the z component of the vector A. This is the vector A. Maybe just for once, I'll throw in a little vector thing there. The z component of the vector A, the partial derivative with respect to the y component. So, of course, if A is a function of x, y, and z, then we know that A is also its x component, A is its y component, and A has a z component, and AX is a function of x, y, and z, and AY is a function of x, y, and z, and AZ is a function of x, y, and z. This just stands to reason, right? A is a vector, it has 3 components. As a vector, it's a function of, as a vector field, it's a function of x, y, and z. As a vector, it has 3 components, so each of the components is some function of x, y, and z, right? So when I say AZ, sometimes if you write AZ, that's actually shorthand for the partial of z of some function A, right? That is typical. But no, what we want it to mean in this case is the component, the z component of the A vector, of the vector A, and we are going to use this notation as partial y. That's the partial derivative of the z component, right? So that's what this is. And this means it's in the x hat direction, and this is the y hat and the z hat. So the way you would write this down is you would do a few things. First of all, you have a plus sign here because you're adding these 3 vector components together now. And this guy here you would write down as the curl of A, the x component, right? And this is the curl of A, the y component, and this is the curl of A, the z component. And this might be the partial derivative with respect to x of the y component of the curl of A. So that's the kind of notation we're using here. All right, so with that in mind, the notation for the divergence is simply the the derivative with respect to x of the x component, the derivative with respect to y of the y component, the derivative with respect to z of the z component. And if the divergence equals 0, this sum must equal 0 for whatever the vector f is. So now here's our statement. What we're going to say is if the divergence of f, if that equals 0, if the divergence of f equals 0, we're making the claim that F is the curl of some other vector field A. We're going to make that claim. And so I need to be able to prove that if this is true for F, then this is true, right? So I should always be able to find a vector A that equals F, that its curl equals F, and that fact must be contingent on the fact that the divergence of F is 0, right? In other words, not every vector field is the curl of something, but if this is true, then this is true. And I'm going to do this sort of by construction. I'm going to actually make the vector A that will be equal to F and depends on this fact. The construction of A depends on this fact. All right? So I'm saying that F, being the curl of A, is literally this thing right here, right? Whatever A is, I've constructed this curl of A right out of the definition. It's literally copying these things here, right? The curl of A right into this definition. And now I'm just calling it F, right? So F is equal to the curl of A. Maybe I should write down, well, here, I've got it right there. I've been writing it several times. So now, all right, so how are we going to do this construction? Well, the first thing we're going to do is take note, and this is what got me off the rails the last time I did this lecture, right? The curl of any gradient is 0. We proved that earlier in this lesson, right? So knowing this fact, and this is true for any function f, any scalar function f, and so remember, f is a function of x, y, and z. It's just a scalar function, right? It returns some kind of number, real number. And so when this is true, I now know that I can take the curl of some vector field. If I add to that vector field a gradient, the curl doesn't change, right? And this is one of the things that's very similar, and you'll see it has to do with gauge freedom, right? Ultimately, when we talk about gauge freedom, this very principle that we're showing you right here is going to surface again. The curl of any vector field doesn't change if you add to that vector field another vector field, which is a gradient of some scalar function. And this could be literally any scalar function that's reasonably well behaved, and the derivatives all make sense. But I find a scalar function, I take its gradient, I can add that to any vector field, and I won't change that vector field's curl. And this is a huge degree of freedom, because there's a lot of functions in the universe, right? So there's a lot of gradients of functions in the universe, and you can add any one of those gradients to a vector field, and you won't change its curl. So we're actually, for this proof, we are going to exploit that fact, right? So let's consider that the vector field we seek, we're going to call it A. It has an x component, a y component, and a z component. And we've literally written, the curl of A we've already written right here, right? There's the z, y, and x component. That's these guys right here. So now I'm writing the notation for A as a triplet, right? This is a vector, the x component, y component, z component. Instead of doing what I kind of move freely between this notation, right? X hat plus a y, y hat plus a z, z hat, right? These two things are essentially the same. It's just how we organize it in order to sort of do the notation, right? Or to do some of the proofs. It's a little easier to not to have to write the unit vectors and the addition. Sometimes it is a good idea. So I feel free to go between those two things, those two types of notations for the vectors. So now what I'm going to do is I'm going to exploit this freedom that I can add any scalar function, right? And I want to find a function f so that the partial derivative, I used a weird notation here. The partial derivative of f with respect to z is the opposite of az, right? I'm going to find some function out there, right? This is a function of space. Remember, az, as I pointed out earlier, az is a function of x, y, and z, right? So this is some function of x, y, and z. This is also a function of x, y, and z. But this is the partial derivative of some function f with respect to z, and I need to find a function f such that that partial derivative is the opposite of the zth component of a. So can this be done? Well, yeah, all you do is you integrate both sides, right? You integrate both sides, and you can just solve this integral and get f, right? That's really not a problem. So as long as az, the zth component of this vector field, can be integrated in principle, you can find f in principle that will satisfy this requirement, right? You won't fully identify f, but you'll get it close enough, right? Because all you got to do is satisfy this. That's our requirement. Now, why do we do that? Well, if I now take f and add its gradient, right? Add its gradient to a, right? Instead of g here, right? Instead of g, I convert all this to a, right? Now, what'll happen? Well, I get a plus the gradient of f. I get ax plus the partial derivative of f with respect to x. That's the x component of this sum, the y component of this sum. But look what happens to the z component. This guy, by construction, we've proven it can definitely be done. That is going to equal minus az, right? That was the construction we just did right here, right? And therefore, this whole term goes to 0, right? And that means that any vector field that I propose satisfies the requirement that I'm seeking, right? That its curl is f. Regardless of what it is, I can always find a function f and execute this transformation by adding a gradient of that function to this proposed vector, and I will get a new one, a new vector a plus the gradient of f, which has no z component, right? So a, I'm going to say without loss of generality, I can say this the z component is 0. And that's a gauge transformation, right? That is a form of gauge transformation. We wouldn't call it a gauge transformation in physics per se, because usually gauge transformations have to do with physical quantities, but this is a gauge transformation in a way. I mean, it's certainly using the same principles. So I'm now going to construct a such that only ax and ay are non-zero, right? And I can do that without any loss of generality. So with that in mind, the next step is just to calculate the curl of a with this, I guess I should say the gauge transformed a, maybe. And so with ax being 0, the x and y components lose half of their sums, right? Because you had an ax in the first piece, and you had you had an az in the first piece, and you had an az in the second piece here. But this third piece of the curl still has partial x of ay and partial y of ax, right? There's no az here, so you still have two pieces. And the vector we're looking for, right? Remember, f is the thing that's supposed to equal the curl of a, right? So f has an x component, a y component, and a z component. And if f equals the curl of a, then these equality signs should look like this, right? F of y is minus the partial of z, the partial of ay with respect to z. F of y is the x component of a partial derivative with respect to z, and f of z is this sum of these two partial derivatives, right? So now we need to find ay and ax. We already know az. Az is 0, and we've done that because we've got that gauge freedom that we've already played with. So I'm writing down what I just said in words, right? The x component of our vector is this expression, this partial derivative. The y component is this partial derivative, and the z component is this partial derivative. And this partial derivative leads to this integral. We just integrate it, right? You integrate both sides, again, just kind of like we did a moment ago, and you find that the integral of the x component with respect to z is minus ay, right? That's simply the integral of this expression. But you pick up a constant, right? You pick up a constant with respect to z, so it's some arbitrary function of x and y only, right? We'll call that alpha. And likewise, you can integrate this, and you end up with, you integrate the y component of the function f. Remember, you know the function f, right? F is what you're trying to find is the curl of something. So you're given f, and we're seeking a, right? So if we are given f, we're given f of x, we're given f of y, we're given f of z. So these are functions, so you can integrate them. But we only need to integrate them with respect to one of its three variables, right? And so whatever ax is, it has to be the integral of f of the y component of x with respect to z. And you pick up, again, a constant. So then f of z, the z component of f, is sort of fixed at this point, right? Because you've solved for y and you solve for x. So f of z you calculate by taking the derivative of ay with partial derivative with respect to x, and the derivative of ax with respect to y, and take the difference between those two, and that's f of z. So you only need to do these two integrations. And then you should get f of x, f of y, and f of z, right? In fact, that's what this next line is. This next line, I literally do this substitution, right? I take this, and I substitute it in here, right? Here's the integral f of x of z, here's the constant, f of y, here's the constant, and you're taking the difference between the two. But remember, a negative sign appeared here. That negative sign came from here. So you have the negative sign and negative sign, and that equals f of z. So I guess this last line here blown up with the substitutions for the substitutions for ay and ax are made here, and you end up with this line right here. And now what we do is notice that the partial derivative with respect to x of an arbitrary function of x and y is still an arbitrary function of x and y. The partial derivative with respect to y of an arbitrary function of x and y is still a function of x and y. So we basically are going to combine those two arbitrary functions together, and we're going to get the partial derivative with respect to x of this arbitrary function, right, is equal to, and now it's just rearranging, it's f of z plus this and f of z plus this, right? And that's what this line is, right? So it's f of z plus the partial derivative with respect to y of f of y, that's this piece, and the partial derivative with respect to x of the integral of f of x, which is this piece. And that is our the partial derivative of our arbitrary constant. So now this, another way of saying it is, let's just assume this arbitrary constant is 0, and we have to solve for this arbitrary constant. That's another way of looking at this, by the way. But this is the solution for the arbitrary constant, right? This is the solution for the arbitrary constant alpha xy. And if we knew that, then we know this. Then we know ay, because we take that integral and subtract this arbitrary, I say constant, but what I mean is an arbitrary function of x and y, and we've got ay. This we have assumed to be 0, so we've got ax. And once we have ay and ax, we have f of x and f of y by taking these partial derivatives, and f of z as well. So that's the solution to the problem in a way. The problem of the solution to the problem is that how do we know this is solvable, right? How do we know that we can actually integrate both sides of this? Well, that's easy. You can, right? You can definitely integrate both sides. There's nothing stopping you. If this is a function, you can integrate the function with respect to x. You can integrate this. This is supposed to be known. You can integrate you'd be integrating both sides with respect to x. So you can integrate this with respect to x. You can integrate that with respect to x. This integral in here is a function, right? So you can definitely integrate it. The problem is whether or not there's a function only of x and y, right, that will result from this. That's the problem. You see, integrating these things in principle definitely can happen, but there's nothing a priori about this that says the result of the integral here, of integrating this guy with respect to dx, right? There's nothing a priori that says that it won't have a z dependence, right? There's nothing about this that eliminates z as a dependent variable. That may not be obvious because you might think, oh, well, wait a minute, I'm integrating f of y dz, for example, right? Well, f of y is a function of x, y, and z. Well, you say, well, I'm integrating out the z, but remember, this is just an antiderivative, right? This is usually written something like z up here, or you might even change the variable, and if you want to be really formal about it, you would write it this way. You would write f of y, which is a function of x, y, and s, ds, and then you put at the top of integration, at the peak of the integral symbol, you put z. And then you kind of treat it like a definite integral, but z returns, right, as part of the limits of integration. This is like a really formal way of looking at it. But that is, the point is z, you can get a function of z out of this. So that's the problem. Is this a function of z or not? Well, the way we know is let's take its derivative with respect to z and hope that it's 0, right? So if you take the derivative of all of this, I've got that integral there, let me get rid of that. If you take the derivative of all of this with respect to z, oops, this is supposed to be, I can write it out this way. Well, the partial derivative of z of f of z is dz dfz. Okay, fair enough. The partial with respect to z of the partial derivative of respect to y of the integral of fy dz, well, you use the fundamental theorem of calculus, right? I'm taking the zth derivative of the antiderivative with respect to z. So because z, and again, this is where the commutation of partials is so important, I slip dz past the dy and I take the partial derivative of this thing with respect to z, and you just get fy. So you get the partial derivative of y, fy. And then again, I do the same thing here, and you end up with undoing this integral with this partial derivative using the fundamental theorem of calculus, and which kind of in reverse, and you end up with fx. So you end up with the partial derivative with respect to x of fx. And so you have partial z fz, partial y fy, partial x fx. Does that equal 0, right? Well, the good news is that is the same as the divergence of f equals 0. So it is equal to 0 only if the divergence of f is 0, right? So that's where we're using the divergence fact. And so if the divergence of f, so now you read it backwards. If the divergence of f is 0, then you can always construct a vector A whose curl is f. That's the proof I was planning to deliver in my last lesson, and I went totally off the rails. Okay, so that answers the key question is, can we write the magnetic field as the curl of a vector potential? And the answer is yes. Okay, so with that in hand, we will now call A the vector potential. Sometimes it's called the magnetic vector potential, but I think that's a little redundant. And it's defined straight up this way. And yes, there is a gauge freedom that we're going to talk about, right? Because clearly I could add to A, as we just saw a moment ago, I could add to A the gradient of any scalar function in the world, and I still get something whose curl, right, is going to equal B. So this is a freedom. This freedom to change A in this very specific way, which is a pretty big freedom because, like I said, there's a lot of scalar functions out there. There's no restriction on what this scalar function is, except for the differentiability and reasonable, physical smoothness or whatever. The point is there's a lot of functions out there where this will work, and so there's a lot of choices for A. And we're going to talk about the key choices and how we can exploit this again. But as far as the proof goes, the proof just says that there is an A out there. And once you have that A, you can change it all you want. You can return that Z component all day long, right? Okay, so with that in mind, what other topics do we want to cover before we talk about the scalar potential, which I actually do in the next lesson? Well, actually, you know what? I think I'll leave it there, right? We've now gotten to the point where we can talk about the notion of this vector potential. In the next lesson, we'll talk about the scalar potential. And I had a whole thing about Helmholtz decomposition, which I'll do in yet another lecture. I did want to point out one other thing that I missed, that an astute observer of the course pointed out a couple lessons ago. I had the Weyl representation. I hadn't switched it, right? So I had this gamma zero matrix for the Weyl representation. I had it written down exactly the same way as I did for the Dirac representation. In other words, these four matrices were the same as those four. Now, it's definitely true that when you put it in this sort of 2x2 form, I wrote it down correctly. So, but I did not, in the 4x4 form, I had it wrong I think it was like 2 lessons ago. So I've corrected that here. So I just want to point out that the Weyl representation is the same as the Dirac representation, except for gamma zero. It's one small little change, but it's a pretty big change. It actually has a lot, it's pretty meaningful, different utility for this thing altogether. We're going to go in through this quite a bit later on. I plan to dive deep into the solutions of the Dirac equation, just because it's kind of fun. But for now, we have covered Maxwell's equations, and we are beginning the potential formulation. The next lesson will be the potential formulation of the electric field, and then I'll probably do a recap of the Helmholtz decomposition rule. Okay, so I'll see you next time.